Quick revision video on oxidation number. So we'll start with the essentials. Oxidation number is based on a set of rules that apply to atoms. The oxidation number is a measure of the number of electrons involved in bonding to a different element. The sum of oxidation numbers is equal to the overall charge of the species. Oxidation number is used when writing formulae and balancing electrons in equations to check that all the electrons have been accounted for. In half equations, the total change in oxidation number is equal to the number of electrons involved. And finally, in redox reactions, so when you combine the two half equations together, the change in oxidation number for the oxidized species must be equal to the change in oxidation number of the reduced species. And that's why when you combine half equations, you get the electrons to be the same. So we'll start with the rules. So I'm just going to run through this table and then we'll look at some examples on the following slides. So rule number 1, all pure elements have an oxidation number of 0, and that's because they're not bonding to anything different. So just 3 examples: Na, oxygen in O2, and Ne. Rule number 2, if you've got a group 1, 2 or 3 element in a compound, so in other words it's bonded to something different, they are always +1 for the group 1, +2 for the group 2, +3 for the group 3. And there's 3 examples there. Fluorine is always -1. And there's 3 examples of compounds with fluorine in. Gets a little bit trickier for the last 3 because we've got the word usually. So hydrogen is usually +1. So there's some examples of where hydrogen is +1. It's not +1 when it's bonded to a metal. So when hydrogen's bonded to a metal in a metal hydride, hydrogen has a -1 oxidation number. Oxygen is usually -2. So there's some examples of oxygen with a -2 oxidation number. However, when it's bonded to fluorine, which is a more electronegative element than oxygen, oxygen has a +2 oxidation number. And in peroxides, so something like hydrogen peroxide H2O2, oxygen has a -1 oxidation number. And then finally, chlorine is usually -1. So there's some examples of where chlorine is -1 for its oxidation number. And the thing to watch out for chlorine is when it's bonded to fluorine or oxygen, so they're both more electronegative than chlorine, chlorine has to have a positive oxidation number. So in this slide we'll look at the 3 steps that we use to calculate oxidation number. So step number 1, you assign known oxidation numbers from the rules. Step number 2, you look at the overall charge, and remember that's got to be the sum of the oxidation numbers. And step number 3 is you calculate the oxidation number for the unknown atom. So the example we'll start with, we'll do 2 of these. So the first one is, what's the oxidation number of chromium in K2Cr2O7, potassium dichromate? So rule number 1, assign oxidation numbers from the rules. So the potassium, remember, group 1 elements always +1, so we've got 2 of those, so I've written +1 twice. Common mistake there would be to say +2 for the 2 potassiums, which is kind of dangerous territory because the potassium, each potassium has a +1 oxidation number. And for oxygen, I've written 7 separate -2s. Rule number 2, so the overall charge is 0. There's no charge, this is not an ion in other words. So basically all of these oxidation numbers have to add up to 0. So far we've got -2 times 7, so we've got -14, and we've got +2 from those 2 +1s. So the 2 chromiums are obviously +12, so if we divide that by 2, we get +6 for each chromium. The second example I'm going to look at is an ion. So what's the oxidation number of manganese in MnO4-? So again we'll do the same thing. Rule number 1, put in the oxidation numbers that we know about from the rules. So there's 4 -2s for those 4 oxygens. The overall charge is -1 now. So we've got basically -8 We've got to be left with -1, so the manganese is going to have to be +7. So I'm just going to finish the video with how to use oxidation numbers when we're naming compounds. That's called systematic naming. So Roman numerals are used to indicate the oxidation number of an element that can exist in more than one oxidation state. So we're going to look at the oxyanions of nitrogen and chlorine. So there's 2 nitrogen oxyanions, so basically just nitrogen and oxygen with a negative charge, and 2 for chlorine and oxygen, again with a negative charge. So we'll start with what we know. We've got 3 oxygens, so 3 times -2. We need to be left with the -1 charge, so that 1 nitrogen must be +5. So this is called the nitrate 5 ion, but we use the Roman 5, the V there in the bracket. The NO2 1- ion now, so again same sort of thing. We've got 2 -2s and we've got to leave a -1 charge, so this time nitrogen is +3, so this is the nitrate 3 ion. Now these have got alternative names which you may have heard. We've got the nitrate ion, so often when the nitrate ion is referred to, it's basically talking about the NO3 1- ion, so that's really called nitrate 5. And the nitrate 3 ion is known as the nitrite ion. But in the exam, they would ask you for a nitrate and then a Roman numeral. So the next ones, the 2 chlorine ones, will do the same thing again. So we've got -2 from that 1 oxygen. We need to be left with -1 charge, so chlorine's got to be +1, therefore this is called chlorate 1. And in the final one, we've got 4 times 2-, so that's 8- from that. We've got to be left with 1-, so this time it's +7, so that's called chlorate 7. And the alternative names for these is hypochlorite and perchlorate. But seriously, don't worry too much about the alternative names. It's literally just the 8 name and the Roman numeral that an exam would be asking for. So the final slide is systematic naming, but we're working out the formula now. So kind of doing it the other way around. So we'll use ions oxides to illustrate this one. So iron can form 2 oxides, iron 2 oxide and iron 3 oxide. What are their respective formulae? So we'll do iron 2 oxide first. So I'm just putting in an Fe and an O. So this time we know that the iron's +2 from the Roman numeral, and we know from the rules that oxygen is -2. So what combination of those two would give us no overall charge, because this is a neutral compound? Well, one of each works, so that's the formula of iron 2 oxide, FeO. Iron 3 oxide, so we'll do the same thing again, an iron and an oxygen, and then put in what we know. So iron 3 means that the iron is +3 oxidation number from the Roman numeral, oxygen's -2 from the rules. And so this time, what combination of these would give us 0 overall charge? At the moment, we've got +3 with -2, that would end up with a +1 charge. So what combination of these is going to leave us with no overall charge? Well, it's 2 Fe's, so that'll get us up to +6, and 3 O's, and that'll get us to -6. So that's the formula of iron 3 oxide. If you want to see how oxidation number can be used to write half equations and redox reactions, you need to watch my quick revision video on half equations.